Hi, chemistry students. Let's talk about balancing some simple redox reactions. Later on, you'll have an opportunity to look at some more complex ones, but right now, we can focus on these simple ones as a way to understanding the whole methodology. So it starts with why we would want to balance a reaction in the first place. And if you recall, there are some quantities in chemistry and in science especially that we find are conserved, meaning essentially that they don't change over time. They can just get kind of rearranged. For example, mass is in the universe is considered to be conserved, but we know that it moves around. So in some places there's more, in some places there's less, but the total amount will roughly stay the same. That happens with chemical reactions as well. During a chemical reaction, we've expected the number of atoms to stay the same before and after. We don't think of them as being really converted into something new unless it's a nuclear process. One interesting aspect of a chemical reaction is that there may be some ions involved. And if there's some ions involved, that means there's charge in our reaction. And we also must conserve the charge. So we've got to conserve the charge, meaning that there's going to be the same amount of charge when we start and when we end. So the end result is the need to balance a reaction both with the number of atoms that we have and the charge. So here's essentially the methodology. First, we're going to assign oxidation numbers to all the atoms to find out which atoms are changing. That means if they change their oxidation number, they might have the oxidation number go down, reduced, okay, or they might have their oxidation number increase, be oxidized. Once we've done that, we can separate our reactions into two half reactions based upon the atoms that are changing their oxidation number. Once that's set up, we're going to balance the mass, which is the actual number of the atoms, okay, that we have of that particular oxidation number in each half reaction. So for each half reaction, we're going to want to do that. Once we're finished with that, we're going to do the same, we're going to do a similar thing. We're going to now balance the charge in each half reaction. So we got to do this twice by adding electrons, and this is going to be the key. By adding electrons to the side with the most positive charge. Most positive doesn't necessarily mean that it is positive. It just means that it's the most positive of the two sides. So if we have a -2 side and a -4 side, the -2 is actually more positive than the -4 side. Once we've balanced the charge on each side, we now need to balance the number of electrons that are transferred from one reaction to the other. That's our next step. And then finally, when we've done that, we can add the reaction together to obtain the overall reaction and balance that way. So here's an example. You might see it just this way in a test. Balance the redox reaction below. It's a redox reaction we can see because oxidation numbers are changing. So let's go through the process of balancing this, and this will be the perfect example for what we're trying to do here. So first, assign the oxidation numbers. Important note is that if we have a species like Br2 here, that's a non-combined species, so automatically the oxidation number is going to be 0 for both of those bromine atoms. Another rule of oxidation number assigning is that ions have the oxidation number that matches their charge. So this is going to be +6. The bromine ion, the bromide, will be -1, and the chromium here will be +2. So we've assigned our oxidation numbers, and I'm hoping that we can see the connections. These guys are connected. It's the chromium with a changing oxidation number, and here we see Br2 and bromide. Both of these with bromine in them. That is also connected in some way. So we're going to separate those into half reactions. Once again, I had these guys connected, and I've converted them into a half reaction. I've made these guys connected, or I've seen that they're connected, and I've turned them into a half reaction. So each of these is a half reaction. When I say each of these, I'm talking about this half reaction and this half reaction. From now on, we'll work with the two half reactions to solve our problem. Our next thing that we have to do is actually balance the number of atoms in the half reaction. So if I look at the first one, I've kind of highlighted this, but there's one chromium and one chromium on each side, so they're already balanced. However, If I look at the second one, there are 2 bromines on the right and only 1 on the left. Therefore, I have to multiply by 2, get that stoichiometric coefficient of 2 in there to balance the number of atoms. So what we've just done is we've done a mass balance. We've mass balanced, which is how we had done it before. However, we haven't done the charge yet, so that's the next step. We need to balance the charge in each one of these. When I balance the charge, I look here at +6 and +2. The more positive side is +6, and so we need to add electrons to it. That's the left side of the arrow here. And we need 4 electrons to balance it out. So the -4 of the electrons and the +6 add up to +2. On the right-hand side, our charge is +2. So the charge is +2 on each side now. In a similar fashion, I've got 0 on this side and -2 on this side. You might get confused here, but there's 2 -1s, which is -2. Therefore, I need to add 2 electrons to the right-hand side, the more positive side, which is 0. Moving on, now that we have that, this is essentially telling us that this bottom half reaction here, which is the oxidation, because of the losing electrons. So the oxidation half reaction down here at the bottom, it only gives off 2 electrons every time it happens. However, our reduction, because the oxidation number is going from 6 to 2, it's getting smaller, it's being reduced, it requires us to have 4 electrons to even run. Therefore, we need 4 electrons before the reduction can occur. To make that happen, this entire reaction is going to have to happen more than once. So this is what we're going to do. We're going to balance the number of electrons that get transferred, and that'll take that into account. So in short, we've got 2 electrons and 4 electrons. To make them equal, I need to multiply the second reaction by this 2 here. So the oxidation reaction, I have to multiply by 2 in this case to make sure that I have 4 electrons in the oxidation happening and 4 electrons in the reduction. So now I have balanced not just the mass, but the charge. And the only thing left to do is to add these 2 reactions together. So if I add them together, the 4 electrons in the top and the 4 electrons in the bottom get canceled out. Remember, it's 2 times the 2 gives us the 4. At that point, we've got 4 bromides, 1 Cr plus 6, 1 Cr2 plus, and 2 bromines. And our answer is right there. Notice, if you add this up, the left-hand side, this entire left-hand side, the charge is +2. The charge on the right-hand side is +2. The number of atoms are equal. I've got 4 bromines, 4 bromines, 1 chromium, 1 chromium. You can double check your answers whenever you do one of these. So that is how you use the half reaction method to balance a simple redox reaction.